Hello and namaste everyone, it's me Sanjeet Thapa Magar. Today in this video, I will solve the numerical of design of main floor beam of design of steel and timber structures. This question was asked in 2018 in Provincial University. We used this WSM working stress method. The IS code is IS 800 1984. So the question is design a main floor beam supporting 3 equidistant floor joists. So this is main beam supporting 3 equidistant floor joists. So here is one joist, here is one joist, and here is one joist. So here is the load from slab, and below slab the joist will support the slab, and this main beam will support the joist. This joist are small beam, and this main beam is large beam which support the load of this joist. Supporting over a span of 12.3 meter. So from here to here it is 12.3 meter. So this distance is 3.15. This is 3, this is 3, and this is 3.15. 3.15 plus 3.15 is 6.3, and plus 6 it is 12.3 meter. Over a span of 12.3 meter as shown in figure, each joist transmit 40 kN on the main beam. Each joist will transmit 40 kN on this main beam. So assuming the self weight of beam to be 1 kN per meter, so maximum bending moment at mid span will be this 40 plus this 40 plus this 40 is 448 12 120 kN. This is the total load, and this is 1 kN per meter. 1 into 1 is the load, and what is meter? 12.3 meter. 12.3, that is 12.3 kN. This usually is 1 kN per meter is self load. So to convert it into load, we multiply by 12.3 meter. This meter and this meter cancels, so it is 1 into 12.3 is 12.3 kN. So this is the point load and this is self load. So this plus this is plus 120. This is 132 132.3 kilo Newton. So this is symmetrical. This is the axis of symmetry. From here it is 3 and 3.15, 3 and 3.15, and it is 40 on both sides. So this is symmetric about this axis. So the reaction will be 132.3 divided by 2. So here it will be, this load are in downward direction, so reaction will develop in upward direction as Newton's third law of motion. 66.15 kilonewton, and here this will be also 66.15 kilonewton for both. So maximum bending moment will be at the center of this beam. So we need to find the bending moment at center, that is bending moment max. So this is 16.15, 66.15. The distance from here is 3 plus 3.15, that is 6.15, 66.15. The clockwise moment we take positive, and this 40 will try to rotate this in this anti-clockwise direction, so negative. This is 40 and the distance between them is 3. Now this is 1 kilonewton per meter, it is UDL. So this is 1 kilonewton per meter. So 1, and this distance is 3 plus 3.15 is 6.15. So the load will be 1 multiplied by 6.15, that is 6.15, and 6.15 6.15, and it will act in the center of this. So the distance between this and this is 6.15 divided by 2. So it will be 6.15 square divided by 2. So the maximum bending moment at mid-span will be 267.9 kilonewton per meter. To convert kilonewton in Newton, we multiply by 1000, that is 10 power 3, and to convert meter in millimeter, we multiply by 1000, so that is 10 power 3, so 10 power 6. Assuming sigma BC to be 160 megapascal. So from code in bending, from code as 800 1984 for bending it is for bending tension and bending compression. For bending tension and bending compression, it is 0.66 Fi is the maximum, and if usually Fi will be 250. We take 250 if not given question, so 0.66 into 250 is 165 megapascal, which is ideal maximum. So maximum we can take 165, so 160, we assume 160. We cannot assume more than 165, so we must assume less than 160. So Z is equal to m by sigma. From bending equation, m by I is sigma by y, which is equal to E divided by R. From these two terms, we need the value of Z. So m by sigma is equal to m by sigma is equal to I will go up, and I divided by y, and this I divided by y is Z. So Z is equal to m by sigma, and in this case sigma BC. So moment is 267.9 into 10 power 6 Newton mm, and this is 160 megapascal. So this divided by this is 1.674 into 10 power 6 millimeter cube. To convert it into centimeter cube, we need to divide by 1000, so it will be 1.674 into 10 power 3 centimeter cube. So multiplying by 1000 gives this point will go here, here, and here, so 1674 centimeter cube. Choosing from Eastern table, so Z required must be greater than 1674 centimeter cube in steel table. So this is beam, so we use I section, and Z should be greater than 1674 in centimeter cube. In centimeter cube. What was the value? 1674. So we can choose this ICMB 500. Yes, ICMB 500 because the Z is slightly greater than 1600 something, so we choose the just higher value. So Z is 1800 8.7 in centimeter cube. 1800 8.7 1800 8.7, we round up to 1810. So this value must be greater than this, so we choose this. So from this IS code, for Fi 250, this is table for Fi 250, and we need the value of capability small t, this is the thickness of lens, this is the thickness of wave, and d1, e, l, and ry. This value we need. T, small t, d1, l, ry. We should take this value from steel table. ISMB 350. No, ISMB 500. ISMB 500. Thickness of lens, that is capital T, and thickness of wave, small t, is this 17.2 and 10.2. 17.2 and 10.2, and similarly 10.2. 17.2. So depth is 500 because we choose ISMB 500, and this is also given here. The depth is 500, and this d1 is 500 minus 2 into 17.2. 500 and 17.2, because in I section this is thickness of flange T of or capital T, so this will be also T. So this is the depth, total depth denoted by capital D or L. So this is D1, which is equal to D1 is whole depth minus this and this, that is L minus 2 T of L is 500 and 2 T of is 10. T of is thickness of flange is 17.2, so it will be 45.6, and L is 3.15, this, and ry is in table ry it is 3.52. So L by ry is 89.49. This is less than 2. 1.686 is less than 2, and d1 by tw is also less than 85. So t by tw is less than 2. For t by tw, this is the case of greater than 2. So in our table, t by tw is equal to or less than 2. So this condition satisfied, and d1 by t less than 85. d1 by tw less than 85. So we should see this table 6.1b of IS 800 1984. Our d by t value is 29.07. 29.07. In between 25 and 30, this 29 lights, so this will be something here. And L by Ry is 89.49. 89.49. 89.49, which lies in between 85 and 90. From table 6.1b for d by t 25. For this d by t 25, first we take 25 and second we take 30 because it lies between 25 and 30. And 30. The L by Ry value is 89.49, which is between 85 and 90. So this we have to calculate. For 85 and 90, sigma BC we have to calculate. For 85 and 90, for 250, we have to calculate this 135 and 131 for 25. 135 and 131. 135 and 131 for 25. So from interpolation we get 131.4 megapascal, and by taking d by t 30 for 85 and 90, d by t 30 for 85 and 90, this 85 and 90, 133 and 129. 133 and 129 by interpolation, sigma BC is 139.4. Now in here we have taken first 29 and then second for 30. So this 29.07 will be in middle of 25 and 30. 25 and 30, 29.07. So for this table we can put this sigma CB value from for 25 d by t 25 it is 131.4, and for 30 it is 129.4. So interpolation sigma BC is 129.77. So Z required is the moment was this, and sigma BC is this. I have already derived the formula of Z, m by sigma. This sigma is assumed, 160 is assumed, but 129 is the required sigma. So it is Z is 2064. For this I section, the Z Z was 1810, 1810, but the required should be 2064 is required, so the sections should be revised. I repeat, by that IC section of ISMB 500, it can resist up to this 1810, but the Z required for this moment is 26.4, so which is greater than this, so the section should be revised with more Z value than 1810. So we have chosen ISMB 550. is in another table. Where is 550? For IS 550, the Z is 2359.8. 2359.8, we round up to 2360. In some table it is 2360, so which is greater than previous Z. So by previous we calculate T of TW D1, we see this D1 TW DT of from this IS code still table, ISMB 550. We calculate this depth is this 550, TW is 11.2, T of is 19.3, 11.2, 19.3, depth is 500, 19.3, and D1 is this 550, depth minus 2 into thickness of flames, that is 45.6, and YAL is 3.15. it is in YAL is in meter. To convert in centimeter, we multiply by 100. RY in this case is RY 3.73, 3.73. So T divided by TW, capital T by small t is less than 2. It is less than 2, and D1 by T is D1 by T is less than 45, less than 45, less than 85. So again we use this table 6.1b. D by T is 28.5, D by T is 28.5, 28.5 lies between 25 and 30, and YAL by RY is 84.45, 84.45 lies between 80 and 85. If not given, we should choose CFI 250 MBA. So first we see this 25 for d by t 25. For d by t 25, L by Ry is 84.45, which lies between 80 and 85. For 80, sigma BC is and for 85. For 80, sigma BC is 138, and for 85, sigma BC is 135. 138 and 35. 138 and 135. By interpolation, we get in between this 135.33. So in this here we choose 25, and here we choose 30. Divide 30. So for 80 it is 136, and for 85 it is 133. 136 and 133. 136 and 133. By linear interpolation, sigma BC is 133.33 megapascal, and for 84.45. This 28.5 lies in 25 and 30. So when we choose 25 and when we choose 30, at d by t 25, sigma BC is 135.33. 25 133.33. When d by t is 30, sigma BC is 133.33. So the value 28 lies between this and this, so the value between this and this will be also 133.33 for common sense. So Z required from previous formula, that is m divided by sigma BC. Formula is m we have already calculated, and sigma BC comes to be 133.33. So this 2 into 10 power 6 millimeter cube. To convert it into centimeter cube, we divided by 1000. So 2 into 10 power 3 is 2000 centimeter cube. 2000 centimeter cube, and this section can provide Z up to 2360. This can reduce up to 2360, and the Z required is 2000, which is less than this 2360, so safe. So next is check for shear. Maximum shear force is, we have already calculated in from figure. Maximum shear force is 66.15 kilonewton. kilonewton. To convert kilonewton into newton, we multiplied by 1000. The shear force, average shear stress formula is shear force divided by area. If this is I section, then the area that registers shear force is all depth multiplied by this thickness. All depth multiplied by this thickness is, all depth is d, and thickness is thickness of wave. This wave on the shear force is restricted by this wave only, so thickness of wave TW is 11.2. TW is 11.2. And there is this 550. This 550 and 11.2, so it is 10.7 megapascal. The average shear stress is given in code. Average shear stress, average. $69. Maximum is 0.45 Fy, but average is 0.4 Fy. 0.4 into Fy, it is 250, so 0.4 into 250 is 100. This should be less than 100, so this is less than 100, so safe. And the maximum deflection, the formula is K. This formula is also given in code. And this formula is given in the code of timber 7.5.9.2 of page number 13. Del is KW L cube upon EIX. So K value is 19 by 384. You have to remember 19 by 384. W is W is 40. Where is 40? W is 40, and L is 1230 millimeter. This 12.3 into 1000 to convert into millimeter. 12.3 into 100 is 1230, so 1230 is in millimeter. So this is in centimeter. This is in 40 is in kilonewton, and this is IX 64893.6 from steel table. IX is 64893.6 centimeter power 4. Centimeter power 4, so this must be in terms of kilonewton, and centimeter. So the value of E is 2 into 10 power 5 Newton per yum square or megapascal. So to convert this Newton into kilonewton, we divide by 1000. So 1000 is 10 power 3. So 5 minus 3 is 2. 10 power 5 divided by 1000 is 10 power 2, and the unit goes to kilonewton per mm square. That is 1 millimeter into 1 millimeter. So 2 into 10 power 2 divided by, this is kilonewton. In 1 millimeter there is 1 divided by 10 centimeter. Similarly, in this 1 meter also there is 1 divided by 10 centimeter. So 2 into 10, this 2 plus 1 is 10 power 4 kilo Newton per this centimeter, and centimeter it is centimeter square. 10 into 10 power 4 kilonewton per centimeter square. 2 into 10 power 4 kilonewton per centimeter square. So this value must come in centimeter, that is 2.83 centimeter, and the allowable deflection is L by 325. So L is in centimeter, 1230 centimeter divided by 325, it is 3.75 centimeter. So this value should not be greater than 3.87. So this value 2.83 is less than 3.7678. So okay. So thanks for watching. Like, share and subscribe the channel.